Infrared spectroscopy is the spectroscopy that deals with the infrared region of the electromagnetic spectrum, that is, light with a longer wavelength and lower frequency than visible light. It covers a range of techniques, mostly based on absorption spectroscopy. As with all spectroscopic techniques, it can be used to identify and study chemicals. For a given sample, which may be solid, liquid or gas, the method or technique of infrared spectroscopy uses an instrument called an infrared spectrometer or spectrophotometer to produce an infrared spectrum. A basic IR spectrum is essentially a graph of infrared light absorbance or transmittance on the vertical axis versus frequency or wavelength on the horizontal axis. Typical units of frequency used in IR spectra are reciprocal centimeters or sometimes called wave numbers with the symbol centimeter inverse. Units of IR wavelength are commonly given in micrometers or microns, which are related to wave numbers in a reciprocal way. A common laboratory instrument that uses this technique is a Fourier transform infrared spectrometer called FTIR. The infrared portion of the electromagnetic spectrum is usually divided into three regions: the near, mid and far infrared, named for their relation to the visible spectrum. The higher energy near IR, approximately 14,000 to 4,000 centimeter inverse, can excite overtone or harmonic vibrations. The mid-infrared, approximately 4,000 to 400 centimeter inverse, may be used to study the fundamental vibrations and associated rotational vibrational structure. The far infrared, approximately 400 to 10 centimeter inverse, lying adjacent to the microwave region, has low energy and may be used for rotational spectroscopy. The names and classification of these subregions are conventions and are only loosely based on their relative molecular or electromagnetic properties. Infrared spectroscopy exploits the fact that molecules absorb specific frequencies that are characteristic of their structure. These absorptions are resonant frequencies, that is, the frequency of the absorbed radiation matches the transition energy of the bond or group that vibrates. The energies are determined by the shape of the molecular potential energy surfaces, the mass of the atom and associated vibronic coupling. In particular, in the Born-Oppenheimer and harmonic approximations, that is, when the molecular Hamiltonian correspond to the electronic ground state can be approximated by a harmonic oscillator in the neighborhood of the equilibrium molecular geometry, the resonant frequencies are associated with the normal modes corresponding to the molecular electronic ground state potential energy surface. The resonant frequencies are also related to the strength of the bond and the mass of the atom at either end of it. Thus, the frequency of vibrations are associated with a particular normal mode of motion and a particular bond type. After studying this module, you shall be able to learn about the basics of IR spectroscopy and their applications in the structural determination of metal carbonyls, bonding mode of carbonyls in their metal complexes, higher stretching frequencies of terminal and bridging carbonyl in metal carbonyls containing terminal bonding modes and their higher stretching frequencies, and differentiation between various conformers of metal carbonyls using IR spectroscopy. Introduction. Infrared spectroscopy has emerged as a useful analytical tool for the accurate identification of various structural features and purity of a chemical compound. One of the biggest advantages of infrared spectroscopy is that the chemical samples can be analyzed in virtually any state. Bonded atom in molecule can vibrate along their bond axis. They can do so in all the three states, namely solid, liquid and gas, particular in chemical bonds where the constituent atoms are not same. The contraction and expansion of such a bond would lead to a change in the dipole moment of the bond. An infrared spectrum is generally obtained by passing infrared radiation through a chemical sample and determining what fraction of the incident radiation is absorbed at a particular energy. A basic IR spectrum displays a graph of IR light absorbance or transmittance on the vertical axis versus IR stretching frequency or wavelength on the horizontal axis. The units of frequency used in IR spectra are reciprocal centimeters, which is also called wave numbers. An increase in wave number corresponds to an increase in energy. The commonly used laboratory instruments are based on the technique called Fourier transformation. Hence, the instrument is called a Fourier transform infrared spectrometer. Two-dimensional IR is also possible. Band intensities can also be expressed as absorbance. Absorbance is the logarithm to the base 10 of the reciprocal of transmittance. You can see here the two atoms, they are bonded together with a vibrating string, and the vibrational frequency is given by the formula nu bar is equals to 1 by 2 pi c under root f m1 plus m2 divided by m1 into m2, where nu bar is the vibrational frequency in centimeter inverse, m1 and m2 are the masses of atom 1 and 2, c is the velocity of light in centimeters per second, and f is the force constant. The peaks appearing in an absorption spectrum corresponds to the vibration frequency of a chemical bond in the sample molecules. The bonds have different bond energies and hence different stretching frequencies. The IR spectrum of a molecule containing various types of chemical bonds show various absorption bands depending upon the type of bond and its stretching vibration. Chemical compounds absorb infrared radiation that corresponds in energy to these variations. The stretching vibrations can be explained by Hooke's law to approximate the stretching frequency of a chemical bond consisting of atom 1 and atom 2. Bonding modes of carbonyls in their metal complexes. CO is a strong ligand and it has a tendency to pair up the electrons of metal atom in the inner orbital, and thus metal carbonyls are inner orbital complexes, and most of them follows 18 electron rule with a few exceptions. The geometry of a metal carbonyl depends upon the nature of hybridization on the central metal. Tetrahedral, trigonal bipyramidal and octahedral are the common geometries for metal carbonyls. In metal carbonyls complexes, carbonyl ligand displays a variety of bonding modes such as terminal and bridging, etc. The structural determination of metal carbonyl complexes is extremely important owing to the existence of a large number of bonding modes. In free carbonyl, the electrons are polarized towards the more electronegative oxygen. For example, the electrons in the pi orbitals are concentrated nearer to the oxygen atom than to the carbon. The presence of a transition metal cation reduces the polarization in the CO bond by attracting the bonding electrons and thereby affecting the stretching of the carbonyl. Moreover, ancillary ligands also affect the carbonyl stretching frequency in their metal complexes. The consequence is that the electrons in the positively charged complex are more equally shared by the carbon and oxygen, giving rise to a stronger bond and a higher energy CO stretch. The bridging modes of carbonyl in their metal complexes are strongly correlated with the position of the CO stretching band in the IR spectrum. Various bonding modes of carbonyls in their metal complexes in this figure. Since carbon monoxide displays various bonding modes, a large number of spectroscopic and analytical techniques have been employed to determine their structural features in a metal complexes such as X-ray diffraction, infrared spectroscopy and electron diffraction studies. Out of these, infrared spectroscopy is the most convenient and cost-effective method of structural analysis because of the reasons. The chemical sample can be analyzed in any of the three states of matter, solid, liquid and gas. Various bonding modes of carbon monoxide in metal complexes exhibit different stretching frequencies and hence display different IR absorption bands. The IR spectroscope is a much simpler and cheaper setup as compared to the other techniques. The analysis of an IR spectrum is easy and provides initial idea about the bonding environment around the metal in the complex. IR stretching frequencies of terminal and bridging carbonyl in metal carbonyls. Mononuclear metal carbonyls have only linear MCO linkages where carbonyl carbon is bonded to only one metal ion. This type of bonding mode is called terminal bonding mode of the carbonyl ligand. In other metal carbonyl complexes where the carbonyl carbon is bridging between more than one metal ions, this type of bonding mode is called bridging bonding mode. These bonding modes display different absorptions in the IR spectrum and hence can be easily distinguished. The terminal carbonyl group exhibit absorption in the range 1850 to 2125 cm inverse, while the bridging carbonyl group does so in the range of 1700 to 1850 centimeter inverse. The number and position of IR bands in metal carbonyls depends on various factors such as geometry of metal carbonyl, molecular symmetry, bonding modes of carbonyl, charge on the metal ions and ancillary ligands. Generally, the IR stretching frequency of the carbonyl ligands depends on the bonding modes. Terminal CO is the greatest, then the doubly bridging CO and then the triply bridging CO. You can see from the table the various bonding modes of carbonyl has the different stretching frequencies. As you can see, for the free carbonyl molecule, the bonding mode of this carbonyl has the stretching frequency at 2143 centimeter inverse. For the terminal MCO bonding mode of carbonyl, the stretching frequency ranges from 1850 to 2120 centimeter inverse. For the symmetric mu2 carbonyl bonding mode of carbonyl, the stretching frequency is from 1700 to 1860 centimeter inverse. For the symmetric mu3 carbonyl bonding mode of carbonyl has the stretching frequency from 1600 to 1700 centimeter inverse. Metal carbonyls containing terminal bonding modes and their IR stretching frequencies. Monocarbonyl complexes only linear MCO linkage, hence only one band in the IR region 1850 to 2120 centimeter. Dicarbonyl complexes. In dicarbonyl complexes, carbonyl can display two possible geometries. In dicarbonyl complexes, a single band in the IR region indicates that the structure of the carbonyl is linear, whereas two absorption bands directs towards the bent geometry where the two bonded carbonyls are not 180-degree angle apart in the complex. You can see here for the linear MCO molecule, when there is symmetric stretching, no change in the dipole moment occurs. It is IR inactive, whereas the bending vibration mode is IR active. For molecules containing two carbonyl ligands on the same metal ion, the relative intensity of the IR bands can be used to determine the approximate angle between the two CO ligands by the equation, that is I symmetric upon I antisymmetric is equals to cotan square of phi by 2, where I symmetric and I antisymmetric are the intensities of the symmetric and antisymmetric stretching frequency bands and phi is the angle between the two carbonyl ligands attached to the same metal ion. The symmetric stretching frequency IR band is less intense as compared to the band due to antisymmetric stretching and hence can be easily distinguished. Therefore, the linear and bent geometries of the carbonyl ligands can be identified simply by their IR signature bands. Complexes containing 3 or more carbonyl ligands. In these complexes, the number of carbonyl stretching frequency bands cannot exceed the number of carbonyl groups present in the complex. whereas it is possible to get lesser number of IR bands than the number of carbonyl groups, which depends upon the symmetry elements present in the complex. More symmetric metal complexes generally display lesser IR bands. For example, the metal complexes of tetrahedral and octahedral geometry generally display a single IR band. In some cases, the IR band may overlap or may be of low intensity. Moreover, the number of bands in the IR spectrum also depends upon the coordination number of the metal ion and the respective position of the carbonyl ligand. For example, in a metal complex with coordination number 6 having 3 carbonyl ligands, there can be only 2 possible stereoisomers possible, namely the facial geometry and the meridional isomer. The facial isomer being more symmetric than the meridional one display maximum of 2 IR bands, whereas the meridional one can display more bands. Hence, the IR spectroscopy can be utilized to distinguish between the various conformers of the metal carbonyl complexes. In the octahedral complexes containing 4 carbonyl ligands, the one where all the 4 carbonyls are planar and in equatorial position, this metal complex being more symmetrical display only one IR band, whereas the one isomer display more number of bands. Interestingly, the pentacarbonyl metal complexes can have 2 types of structures. The pentacarbonyl metal complexes may display trigonal bipyramidal geometry. The complex can also display octahedral geometry containing 5 carbonyls and 1 other ligand. Both the complexes can be easily identified with the help of IR spectroscopy. In general, the trigonal bipyramidal complexes display 2 IR bands, whereas the octahedral complexes display 3 IR bands. Let us summarize. Infrared spectroscopy is the most convenient and cost-effective method of structural analysis of metal carbonyl complexes. CO is a strong ligand and it has a tendency to pair up the electrons of the metal atom in the inner orbital, and thus metal carbonyls are inner orbital complexes, and most of them follow 18 electron rule with few exceptions. Carbon monoxide generally shows terminal and bridging bonding modes in metal carbonyl complexes. The terminal carbonyl group exhibits absorption in the range 1850 to 2125 cm inverse, while the bridging carbonyl group does so in the range of 1700 to 1850 cm inverse. Monocarbonyl complexes have only linear MCO linkage, hence only one band in the IR region 1850 to 2120 cm inverse. In the dicarbonyl complexes, a single band in the IR region indicates that the structure of carbonyl is linear, whereas 2 absorption bands directs towards the bent geometry where 2 bonded carbonyls are not 180 angle apart in the complex. In octahedral tricarbonyl complexes, the facial and the meridional isomers can be easily distinguished by the IR spectroscopy.